Salam and welcome everyone. So in this video, we're going to be doing another physical chemistry question from the Atkins Physical Chemistry Thermodynamics 11th edition textbook. So in this video, the question we're doing is what we see on the screen. The molar volume of a certain solid is 161.0 centimeter cube per mole at 100 atm and 350.75 Kelvin. Its melting temperature. So the melting temperature of the certain solid that we're dealing with has 350.75 Kelvin. Now, we're also told that the molar volume of the liquid at this temperature and pressure. So basically, the same temperature of 350.7 kelvins and the same pressure of 1.00 atmosphere, we have a different molar volume of 163.3 centimeter cube at 100 atmosphere. This is the next part of the question. The melting temperature changes to 351.26 Kelvin. Calculate the enthalpy and entropy of fusion of the solid. So the first thing you have to do, like we do in any chemistry question, is for us to break down the information and write out the parameters. So we're told that for a particular solid, we have, so we're going to do the solid first. We have molar volume to be 161.0 centimeter cube per mole at 1.00 atmosphere. So pressure is 1.00 atmosphere. And then temperature is 350.75 Kelvin. Now, they said the molar volume of a liquid at this temperature and pressure. So now we're dealing with liquid. That's literally the main difference between both information. We were told that the molar volume of the liquid at this temperature, so the pressure is still going to remain the same, as well as the temperature is going to remain the same. So 350.75 Kelvin. So they're told that the molar volume is now one, is going to be 163.3 centimeter cube. We also know that whenever we're dealing with like a change in volume, pressure, and temperature, we already know that it has to be like a V final and a V initial. We see that this is a process of melting, going from solid to liquid. Hence, we would have a situation where we have an initial volume and a final volume. So the molar volume for the initial is 161. So I'm just going to put initial here or ini here. And then the one for the final is 163.3. So we're just going to put a FIN here to indicate initial and final. So that's that. Now we're told that at 100 atmosphere, the melting temperature so changes to 351.26 Kelvin. So now we have a melting temperature after a process occurred. We have a melting temperature that has changed as well as a melting pressure that's also changed, right? So we have P star, we're going to call it P star as the new pressure, which is 100 atmosphere. And then we have T star as the new temperature. So this is 351.26 Kelvin. Now we're asked to determine the enthalpy and entropy of fusion. So they want us to determine the change in enthalpy and entropy of fusion. So basically what we are asked to determine is the change in enthalpy of fusion and then the change in enthalpy of fusion as well as the change in entropy of fusion. So this is basically what we have. Now, if you've been doing your physical chemistry correctly and if you've been paying attention to your textbook, this is a question from chapter 4B. And what you're supposed to basically do is to use your knowledge from chapter 3 and chapter 4 and solve this question. Now, in physical chemistry, in order to make your work easy, you always have to think of different formulas to actually solve a problem. The formula that I can think of now is the formula we get from the slope of liquid boundary after we've integrated the slope of liquid boundary. So the formula in this question is actually going to be P equal to P star plus the change in enthalpy of fusion, okay, divided by T star, and then the change in molar volume of fusion, okay. All of this here multiplied by, so all of this information in this side multiplied by T minus T star. So this is basically the formula we're going to be using. I know that we're getting to the more advanced part of physical chemistry, but this is basically the formula you're supposed to use. So now Since we have this, the first thing we have to notice is that we have to make sure that we have to be able to differentiate what we have from what we don't have. We've got our P here, which is this 1 ATM. We've got our P star, which is 100 ATM. We're supposed to look for this right here. So this is not for fusion, sorry. Change in molar volume. So let me rewrite this. So the formula here, I apologize, I have to correct this, is the change in molar volume of fusion. I mistakenly put entropy instead is molar volume because we can't have two unknowns. I did not know why I made that mistake, but we're supposed to find the change in molar volume of fusion. Anyways, so we've got P, we've got P star, we've got T star, right? 351.26. So we've got this one right here. We've also got regular T, which is 350.75. So really what we don't have here is the change um, in enthalpy of fusion, which is what we're solving for. Neither do we have the change in molar volume of fusion. But we have to remember something. We've been given two different molar volumes. One when we're in solid phase and another one when we were in liquid phase. And we know that all we have to do whenever we're solving for a change in something, so change in volume of fusion, or change in molar volume of fusion, or change in molar volume that accompanies melting is also another way you can call it, is going to be the final volume, molar volume. So the final one minus the molar volume of the initial. So that's basically it. So we have 163.3 centimeter cube per mole. So 163.3 centimeter cube per mole minus 161, that's initial right here, zero point 0 centimeter cube per mole. So 161.0 centimeter cube per mole. So change in molar volume fusion would be 2.3 centimeter cube per mole. So yeah, this is basically what we have so far. So yeah, this is it. Now, since we now have this value, we can now properly substitute in order for us to use our formula to actually calculate the enthalpy of fusion, the change in enthalpy of fusion. So yeah, that's basically it. But before we go ahead and do that, we have to remember, right, that whenever we're dealing with change in enthalpy or just enthalpy, we're dealing with joules. That's one thing you have to remember in physical chemistry. We have to be extremely careful with our calculations. You may know the formula does not necessarily mean you're doing the work right? Like for example, what I'm trying to say is we're asked to find the change in enthalpy of fusion, right? We know that the units of enthalpy as well as entropy tends to have joules, right? It's not like the basic perfect gas equation where you could have ATM, you could have decimeter cube. Now, anytime you're dealing with joules, your pressure always has to be in pascals, okay? Or you can say Newton per meter squared, and your volume always has to be in meter cube. Now we've been given this information here in centimeter cube per mole. So what this is telling us is that we have to change our volume from whatever we're given to match meter cube, and our pressure to whatever we're given to either match pascals or Newton per meter square. So when we go back to our question, before we start to substitute all of this information here, we just have to try to make sure that our pressure and our volume have the proper units. We don't really worry about temperature because temperature is either Kelvins, Celsius, or Fahrenheit. And many times in science, it's always Kelvins. You hardly ever see them even giving you questions in Celsius, except if you're required to convert it. So temperature doesn't have multiple units, unlike pressure where you have like torr, you have psi, you have bar, you have pascals, you have you have a bunch of them. You have even more than that, right? So yeah. So now we have to convert, okay? And if you don't understand what I've been doing so far, honestly, just listen to the whole of the video and then rewatch it. It's going to be easier for you to understand. So we're going to go now from centimeter cube to meter cube for the change in molar volume, or sorry, the molar volume, or change in molar volume of fusion. So we're going to say centimeter cube per mole. We're trying to get it from centimeter cube to meter cube. So centimeter cube per mole to meter cube per mole. So that would be 2.3 centimeter cube per mole. I'm going to be using dimensional analysis to be able to do the conversion. We have centimeter cube at the bottom, we have meter cube up top. So to do that, we know that 1 meter cube is going to give you 1 million centimeter cube. So this is it. 1 meter cube will give you 1 meter cube will give you 1 million centimeter cube. You can cancel out the centimeter cube. So this is going to be 2.3 times 10 raised to the power of negative 6 meter cube per mole. So this is it right here. So change in molar volume of fusion is going to be 2.3 times 10 raised to the power of negative 6 meter cube per mole. So that's it. So now we have that. Now, of course, we have to convert pressure. We have pressure here in terms of 100 atmospheres. We have another pressure in terms of 1 atmospheres. So we go now, we convert pressure. We have P is 1 atmosphere. Okay, 1 atmosphere, we already know that to be 101,325 pascals. And of course, we have P star, okay, is simply equal to 100 atmospheres. So 100 atmospheres to Pascal. So you have 100 atmospheres, okay, times you've got 1 atmosphere at the bottom using dimension of analysis. You have 101,325 pascals. Don't forget, we're trying to convert, cancel out the atmosphere, cancel out the atmosphere. So what you end up actually having would be 101,325 times 10 to the power of 2 pascals. We're going to rewrite this when we start calculating. We're not going to leave it like this. But anyways, you get the point, right? So that's it. Now we have all that we need, and we can now rewrite the formula and substitute. So the formula we have is P is equal to P star plus change in enthalpy of fusion, H, divided by T star, change in molar volume of fusion, multiplied by T minus T star. So that's it. So yeah, that's basically what we're doing now. Now we can go ahead and like just use this, but I want to try to make sure our work is as neat as possible rather than us putting a bunch of stuff. Let us try to rewrite this formula, okay, in terms of the change in enthalpy of fusion. Okay, this is what we're going to use. We're going to rewrite all of this formula so that our work is not cumbersome and rough. So to do that, we just do a little bit of math here. P minus P star, because we're going to take this one over here, is going to now equal change in enthalpy of fusion, okay, times T minus T star divided by T star, change in molar volume of fusion. Of course, I cross multiply. When I cross multiply, I end up with P minus P star, okay, T star, change in molar volume of fusion is now going to equal change in enthalpy of fusion, okay, times T minus T star. Okay, go ahead. Since we're trying to do everything in terms of we cancel both sides of the equation by T minus T star. We do that. Cancel this out, cancel this out. So our new formula that we're actually going to be substituting our work into is going to be a change in enthalpy of fusion is equal to P minus P star times T star times change in molar volume of fusion divided by T minus T star. Yeah, perfect. This is our work. This is our work. This is our work. This is our work. So yeah, now we can happily substitute. So we've got change in enthalpy of fusion is now going to be P minus P star. So that's going to be, what is P? We know our P to be 101,325 Pascal. 101,325 Pascal. We also know that Pascal is the same thing as Newton per meter square. Since we're doing calculations now, we're going to convert it to Newton per meter square because our volume is going to be meter cube, and we have to be able to cancel out. So we're going to change our Pascal and actually write it in the proper scientific form of Newton per meter squared. So I'm going to put Newton per meter squared here minus the P star, which is just 101,325 times 10 to the power of 2. When we do the calculation, we're just going to add 2 zeros at the end of it. So it's going to be 10,132,500, okay, Newton per meter squared. Okay, you guys, this is just this part of our work. This is only what we've done so far. Okay, so times T star, which is just 351.26 minus, so T star, 351 Kelvin, and then multiplied by the change in molar volume of fusion, which is 2.3 times 10 to the power of negative 6 meter cube per mole. So times 2.3 times 10 to the power of negative 6 meter cube per mole. All of this divided by T minus T star. So that would be T minus T star. 350.75 Kelvin minus 351.26 Kelvin. 0.75 Kelvin minus 351.26 Kelvin. So this is basically how our work is done. So of course we're going to do our math. So we have the change in enthalpy of fusion is going to be 101,325 minus 101,32500. So when we subtract 101,325 minus 101,32500, we end up getting 10,031,175 Newton per meter squared. So that's that. So times 351.25 Kelvin, 26 Kelvin, I apologize, times 2.3 times 10 to the power of negative 6 meter cube per mole. All of this divided by 350. By the way, it's not 10 million, it's going to be negative 10 million. So I forgot to add that. Let me quickly add that here. So I end up with negative 10 million, 31,175 Newton per meter squared. So, and next we have 350.75 minus 351.26. When you input that in your calculator, you get negative 0.51 Kelvin. So, of course, the next thing we do with our knowledge of math is to cancel stuff out. So, we cancel out meter squared. From meter cube, you remove it, you have the meters here. You cancel out the Kelvin here as well. So, yeah, that's basically what you have. So, you have 351. So, you have 10, 0, 31, 175 times 351 times 2.3 times 10 to the power of negative 6. So, the numerator ends up becoming 8,098.1676. So this is Newton over here, and this is meter. So we know Newton meter is also the same thing as joules. So you can write Newton meter or just joules. And then we have a mole here. So Newton meter per mole. All of this divided by 0.51. And the reason why it's 0.51 now is just because the negative here from the numerator cancels the negative from the denominator. So you end up with a positive answer overall. So this is going to be equal to 15,878.7599 Newton meter per mole, or let's just call it joules per mole. So this is basically the answer to this question. So all that we've been doing to find the change in enthalpy of fusion, and so we end up getting 15,878.7599 joule per mole. But our work is still not done because we're chemists and we have to make sure our work is always as neat as possible. So we have to go back and check the lowest number of sig figs that we're supposed to have. So when we go back to our question, we see that we've got what we used to solve the question. We've got here we've got 4 sig figs, we've got 3 sig figs, 5 sig figs, 3 sig figs here, we've got 5 sig figs. So we're going to pick the lowest number of significant figures. That's what we're going to put our final answer in. So we end up rounding this up to 3 sig figs. So we end up with 15.9 kilojoule per mole. So I converted from joules to kilojoules. So basically divided by 1,000. So it's going to end up being 15.9 kilojoule per mole. So this is the answer for the change in enthalpy of fusion or enthalpy of fusion. Now with this information, we're asked to actually solve the second part of the question where we're told to calculate the entropy of fusion of the solid. So now we're asked to find the entropy of fusion of the solid. So before we go on to solve for the change in entropy of fusion or the entropy of fusion part of the question, I need to talk about some theoretical parts of this topic so that it's easier for you to grasp. In the previous chapter, chapter 3 of the textbook, you'd see that there is a very unique like formula. You know, we're so to solve the entropy of fusion. In the previous chapter, there's a formula called entropy of phase transition, which is the entropy of transition or change in entropy of transition is equal to the change in enthalpy of transition divided by the normal transition temperature. So anytime you have a situation where there are phase changes, meaning from one phase to another, in this case from solid to liquid, or you can have liquid to gas or whatever the case is, you have to use, if you're asked to find the entropy of, for example, in this case, entropy of fusion, we're going to use the entropy of phase transition formula. So knowing this information, the formula we're going to use to solve for the entropy of fusion is going to be change in entropy of fusion is equal to the change in enthalpy of fusion, okay, divided by the transition temperature. Now you're going to be wondering, what is the transition temperature? If you look back at our work, we've seen that transition temperature, if you look back at our work, we're going to see that we have two temperatures. We have the temperature of 350.75 as well as a temperature of 351.26 Kelvin. And you're going to be wondering, are we supposed to use the T star temperature or the T temperature? Well, the way you determine the temperature to use is to remember that the normal transition temperature is defined as, yes, we're doing some theoretical normal transition temperature is defined, okay, very important, as a temperature at which two phases are in equilibrium at 1 atmosphere. So we have to look for the temperature at which the two phases are in equilibrium at 1 atmosphere. So we go back to our question now in order for us to determine the temperature. We have the molar volume of a certain solid is blah 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 at 1 atm, okay, and 350 at which 350.75 Kelvin. It's not the temperature. Then we go back again. The molar volume of the liquid at this temperature and pressure. So now we see that 1 atm is occurring in two places. So the transition temperature here, sorry, the transition temperature here is going to be temperature where transition takes place at 1 atm, aka the points where the equilibrium, two phases are equilibrium here. The solid and the liquid phases are at equilibrium at 1 atm, and the temperature that coincides to this pressure is 350.75 Kelvin. So we're going to be using the temperature 350.75 Kelvin. So here, the temperature that we'll be using is the T, which is 350.75 Kelvin. And of course, the enthalpy we're going to be using is what we've solved for previously. So enthalpy of fusion, H, we know that to be 15.9 kilojoule per mole. But again, as scientists, we do not round up until the very end. So we're going to be using the raw answer to do further calculations. When we're done with the further calculations, then we can now approximate. We do not approximate or estimate using raw values, especially if we're still using the same raw values in calculation. So we're going to put 15,878.7, let's just say 0.76. So 15,878.76 is going to be what we use. So that's going to be joule per mole. So doing the calculation, the entropy of fusion is going to be 15,878.76 joule per mole, okay, divided by the transition temperature, which is 350, or temperature of fusion, 0.75 Kelvin. So when we do this, we do the calculations, input the information in our calculator, we end up getting the entropy of fusion to be 45.2709 joule per mole Kelvin. So that's what we get. But then again, we are scientists. We know as scientists, we are supposed to always keep our work in the proper number of sig figs. We see that the enthalpy of fusion is actually in 3 sig figs. So we're going to round up our entropy of fusion to be in 3 sig figs, or we can just remember our question up top. We see that we've got three in our question, we've got part of the question in 3 sig figs, in 4 sig figs, in 5 sig figs. We put the lowest number of significant figures, which is 3 sig figs. So we're going to round this up to 3 sig figs. So what we end up with is change in enthalpy, sorry, change in entropy. I don't know why I keep saying enthalpy. Change in entropy of fusion becomes 45.3 joule per mole Kelvin, or 0.0453 kilojoule per mole Kelvin. So this is the answer to the entropy of fusion. So this is the end of the video, you guys. If you have any questions, I beg you to please put in the comment section. I am here to help you. And if you have any concerns as well as suggestions on how to improve the questions, the channel, make sure you also put in the comment section.
If you're a student who is struggling with any of your STEM related courses, whether you're in middle school, high school, or college, I am the tutor for you. I help students succeed in all their STEM related courses, whether you're in middle school, high school, or college. So if you love my way of teaching, you can just simply email me at chuhabitutoring@gmail.com, and I'm going to try my best possible to help you. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.